All right, this is a little more work we'll be doing with linear functions in slope-intercept form. These are a couple challenges and then a real-world connection. What I encourage you to do is to pause the video, give these a try on your own, see how you do, and then check back in and follow along. So we'll start off with a couple challenges, and the challenges are to convert the following linear functions into slope-intercept form. So remember, we want to get a y equals mx plus b form. Okay? Really, that means isolate for y. Okay, so for the first one, we can subtract 3x from both sides. And let's see what we get. We get a 2y. Remember, the negative 3x and the 4 are not like terms, so we need to write them out as separate terms. Okay, and then we can divide by 2. So we have a y equals negative 3 halves x minus 2. Okay, remember, slope is, I think, a little more convenient to represent as a fraction if you have the option. Next one. By the way, before I do the next one, these are just a preview of the next couple forms of linear equations that we'll be doing. So this form is called standard form, and it has some of its benefits for sure. This form is called point slope form. So one of the things we'll be doing as we work through linear equations is just converting between the two different forms. They have different advantages and disadvantages. But for the second one, the point slope form equation, I want to distribute this negative 2 first. So I'm going to get y minus 3 equals negative 2x minus 6. And then we can add 3 to both sides. And the 3 is going to combine with a negative 6. And we get a y equals negative 2x minus 3. Okay? So that's the equivalent slope-intercept form of the point slope form we were given. All right, next one, a little bit of a real-world connection, and these are rough real-world numbers. My wife used to do some environmental advocacy work with black-footed ferrets and prairie dogs out in the western slope of Colorado, so I thought I'd throw this problem in. There's a picture of a black-footed ferret, super cute right there. So they're an endangered species in Colorado, and they were once thought to actually be fully extinct. But in 1981, a population of 6 breeding ferrets was found. And in the year 2020, so that's the current year that I'm filming this video, there were an estimated 600 ferrets. And so let's assume the population grows linearly. It probably really doesn't. It probably grows exponentially. But let's work with a linear pattern here. Let's try to estimate the number of ferrets in 2030. Okay, so I think your first step here is to deal with the years. And so dealing with years that are in the thousands, 1,981, 2020, 2030, those are a little bit trickier numbers to deal with. So I'm going to define my variable as let x equal number of years. And I'm going to say since 1980. I think that's going to give me some nice round numbers to work with. Okay, and I could have said since 1981 or whatever. Okay, so this value of x right here is actually year 1. I don't know if that shows up. This value of x is year 40, and this value of x is year 50. Okay, so we've sort of converted our years into a different scale. So we have a couple points that we can deal with. We have a point in year 1, we had 6 ferrets, and in year 40, we had 600 ferrets. So we can find a slope, we can find a y-intercept, we can find an equation, and then we can plug in our predicted year for year 50 to find the predicted number of ferrets. So let's find our slope first. So remember, slope is 6 minus 600 all over 1 minus 40. And remember, it doesn't matter in what direction you subtract as long as you're consistent with it. So we have a negative 594 over a negative 39. Our negatives will cancel, so we'll have a positive slope, which is good, meaning ferrets are increasing in number. And that slope is going to be 15.23. I've said before that slope is often easier as a fraction, but an exception to that is when you're dealing with real-world numbers. It's often easier to have slope as a decimal, and I rounded that slope to a couple decimal places. So let's find our equation. So we have y equals mx plus b, and I'm going to use our simpler x-y ordered pair of 1 and 6. So 6 farads equals 15.23 times year 1 plus b. Okay, and we can solve for b. b equals negative 9.23. So this is a kind of a curious result for b. It says that in year 0, so in year 1980, we had negative 9 farads, right? Obviously it doesn't make sense in the real world, but it's still helping us adjust our overall linear equation to fit the data that we have, okay? It also probably speaks to why the farads are probably growing in an exponential pattern and not a true linear pattern. So let's write out our equation. We have our equation is y equals 15.23x minus 9.23. Just checking my numbers. Okay, looks good. And we can take this 50, we're trying to predict into the future. Let's predict for year 50, which is 2030, how many farads we'll have. And we will just plug in, let me get a different color here, this 50 in for this x right there. Okay, and we'll see what y ends up being. So y equals 15.23 times 50 minus 9.23. And we get our y is equal to 752.27. So about 752 farads in the year 2030. Okay, so that's good. They're growing. They're getting a greater population, and it seems like they're recovering. All right, that's a good place to stop right there.